This is lesson 10 at the end of unit 4. We're looking at quadratic systems today. You can see in our 3 pictures that we have 3 different solutions to a quadratic equation and a linear equation in a system of equations. Here, the parabola and the line intersect in 2 places, so it's a possibility that we could have 2 solutions. In the middle example, you see that the parabola and the line intersect in 1 point only, right here at 2, 4, so that's a possibility of 1 solution. And then the final example shows that there is no solution at all. The parabola is clearly below the linear equation, and they would never intersect. So looking at example 1, let's solve a linear system by graphing. So we want to graph y equals x minus 1. I'm going to graph the line first. X minus 1 is just a linear function going through here. And x squared minus 5x plus 4. We can solve that by factoring. Y equals x minus 4 times x minus 1. So we have zeros at positive 4 and positive 1. We also know that the vertex is located at the opposite of b over 2 times a, so 2.5. And we know that the y-intercept is at 0, 4 from the c value. So if our axis of symmetry is at 2.5, and we're 2.5 away over here, then we need to be 2.5 away to the right, which puts us on top of the line at the ordered pair 5, 4. So we're also on the line at 1, 0, and the parabola is going to go through here some way. It's going to have a turnaround point somewhere at 2.5, not sure how far down. But we're only interested in the intersection points between the system. So we have a solution at 1, 0, and we have a solution at 5, 4. So those 2 points are the intersection points between the linear function and the quadratic function. Example 2, we're going to take that as a different approach and use the substitution method. If I set both equations equal to each other, since they're both equal to y, then we know that equation 2 is equivalent to equation 1 because both equations are equal to y. Solving for x, I want to bring the x squared term and then the plus 3x and plus 1x to the left, and 5 minus 10 is minus 5, so we can factor this polynomial x squared plus 4x minus 5 by considering factors of negative 5 that add up to positive 4. So I believe positive 5 and negative 1 would give the product of negative 5 and would also give us the sum of positive 4. So we have 2 solutions when x is negative 5 and also when x is 1, but we need to find the coordinates for the ordered pairs. So by substituting into equation 2, y equals x plus 5, when x is negative 5, y is 0, and then when x is 1, y is 6. So we have 2 ordered pairs where our line and parabola cross, and those solutions would be at negative 5, 0 for the first ordered pair, and also at positive 1, 6 for our second ordered pair. So those 2 functions intersect at those locations. Example 3 is also an example of solving by substitution. It would be a good chance for you to turn off your video and try on your own, and then come back to check your work against mine. Setting each equation equal to the other, x squared minus 4x plus 5 is equal to negative x squared plus 5 That leaves us with 2x squared minus 4x equals 0. The 5's are eliminated. Factoring out a 2x, we have x minus 2. So the x-intercepts are at 0 and positive 2, but we need to use those values in our equation. I'm going to use it inside of equation 2. It's a little simpler. So when y is negative x squared plus 5, when x is 0, y is 5. So we have one ordered pair for the solution at 0, 5. And then the other ordered pair, when x is 2, then y is 1, since we have negative 4 plus 5, so y is 1. So our other solution is at the point 2, 1. Example 4 is asking us once again to revisit the graphing calculator and solve by using that intersect feature. And we're graphing x squared minus 5x plus 2. So on my calculator, it looks like we have somewhere in here, I'm just sketching off of my calculator, and it looks like it's somewhere about a little, almost a 3. So we've got this going on. We know that it crosses the y-axis. This is equation 1 at positive 2. So we have this situation with our first parabola. And again, I'm telling you that's just a sketch. In equation 2, it's an upside down parabola that shifted up 4 units. And the slope is down. So that parabola is going here. And our job is to find the intersection point. So we're looking for this point here. We'll label that x1, y1. And we're also looking at this point here, x2, y2. So using that intersect feature or finding the 0, the x sub 1, y sub 1 ordered pair looks like it's about negative 0.351 and positive 3.88. Then our second ordered pair, using this intersect feature again, looks to be about 2.85 and negative 4.13. So I'm a little bit off here since that's 4, would be a little below that. But the intersect feature is a great way to find systems of equations coordinates. Example 5 wants us to solve the solution of the system of inequalities. So these we need to graph. The first equation, and we also need to shade. The first equation, negative x squared minus 4x plus 3, is going to cross at 3. We know that the hk value can be found by the opposite of b over 2a, and a is 1, so that's going to put us at negative 2. This is the h value, negative 2. And substituting negative 2 into the equation, we would get the opposite of negative 2 squared minus 4 times negative 2 plus 3. So this is going to give us that y-coordinate, or the k value. 8 minus 4 is 4, plus 3 is 7. So we're at negative 2, 7 is our vertex point. Now I'm going to erase that because we don't need that. So we know the hk, without using the calculator, is negative 2, 7. And we're going down 1 and then down 3. So we've got 2, 3, 4, 5, down 5. So that gives us a parabola opening downward. It's a solid line since we have less than or equal to. The shape of the parabola looks like this. We need to shade. So equation 1 is a solid line, and we're shading below the parabola. So let's shade that with some yellow. Solid shaded below. And then we'll move to x squared plus 3. That's a little easier to graph. X squared plus 3. That's going to be, equation 2 is going to be a dotted or dashed line. And we're going to shade above that parabola. And that parabola moves up 1 and then up 3, left 1, up 3, right 1. So we have a parabola with a dotted or dashed boundary line. Shading above that parabola in a different color, let's use green. And you can see our intersection point is between the two intersecting colors. And that intersection is right in here. So those are our solution sets there. Now in our last example, we have a little bit of a challenge. So I took equation 1 and I got y alone. Then doing the same thing for equation 2, we have y alone. Our job is to find the intersection point. So first thing, just like previously, we want to solve the equations so that we have an x value. And since they're both equal to y, we can set equation 1 equal to equation 2 by the transitive property or by substitution. And then getting x squared plus 5x, and we'll subtract 3x, so that'll give us 2x. And then 2 minus 5, that's going to give us negative 3. This polynomial will factor as x plus 3 as one binomial and x minus 1 for our other binomial. We have the solutions for x. So now we know when x is negative 3, the line will pass the parabola. And when x is positive 1, the line will intersect the parabola. But next and finally, we need to find the solution points. So substituting into, I don't know, let's use equation 1. That seems to be the easiest. 3x plus 5. So when y is 3x plus 5, and we use x is negative 3, then negative 9 plus 5 is 4. So we know y is negative 4. So we know one solution point is at negative 3, negative 4. The line and the parabola intersect. And then our last solution, using the same equation again, when y is 3x plus 5 and x is 1, 3 times 1 plus 5 is 8. So y is 8. And our final solution point would be 1, 8. So the parabola and the line will intersect at those 2 points. And we are finished with chapter 4.